we acquire that DLL intact with the import address table, and I'll actually show you that, hopefully, time permitting. Finally, we acquire code corresponding to injected threads, and we'll acquire shellcode if it's still in the stack and heap, which will allow for analysis later. So we got this process acquisition working, and it's cool, but what can you do with it once you have it? Once you've acquired the process on disk, obviously you can stick it in IDA, which is what most people are going to do. But let's take it a step further. Let's come up with something that's a little cooler. So I wrote this tool called Find Executable Code. It's a prototype, which means it's not being released here. It's still got some bugs and some fix-up things that need to occur. But basically, the goal is to successfully, and some of you, for who you guys work for, may have thought about this problem. We want to successfully identify shellcode in memory, injected DLLs in memory, and injected threads in memory. And we want to be able to do it on shellcode that's 9 instructions small. Size shouldn't be, our algorithm should be independent size. We need a successful way to do this. And there are a lot of people who've tried to, and we think we've come up with a solution for it. Basically, one of the biggest problem you have is that you need to be able to differentiate garbage in memory that translate to valid instruction, that translate to valid x86 from injected x86. So you need to make sense of what you're reading and say, well, this sequence translates correctly, but it doesn't make sense. And that's the problem most people run into. So I'm going to tell you how we do it. Our algorithm consists of breaking up the file. We work on a flat file. We don't work on live memory. So hypothetically, Word docs, things like that, this algorithm will work. You break the file up into 256-byte chunks. We take that chunk. We do entropy analysis. We say, in tests we found that entropy value of 3.5 or greater is a great indicator that there's x86 instructions. We may find, all these values are highly configurable. This is what we found in real-world cases, and we're only using real-world cases. We're really not developing our own solutions to prove our theory. We're trying to take malware we find on customers' computers and determine that, hey, this tool still works. So we say 3.5 is the entropy. Once that passes that check, we then say, we found that there are a lot of strings in memory. You've got your environmental block on the heap. That has a lot of strings. That'll throw entropy way off. So we do a string ratio. We say if the percentage is greater than 50%, that there's a contiguous 128-byte string, either Unicode or ASCII, we discard it. And I'll take a moment here to stop and say, if you use ASCII shellcode encoding, what will happen is we'll have our 256 bytes will be a complete string, and I'll have 100% disassembly ratio to that string. And that's a perfect indicator that I've got ASCII shellcode on my stack or heap. So the ASCII factor that we discard, there is a check to figure out that we're not discarding actual x86 code. We then use our own disassembler called NickDasm. The name is subject to change, and it's named after the person who wrote it, Nick Harbour. And this ensures load false positives. What this disassembler does is it says from offset 0, disassemble. Then from offset 1, disassemble. From offset 2, we brute force disassemble, and then we pick the best disassembly. In some cases, there's no valid disassembly, and we discard the 256 bytes. If there is, we then continue with that disassembly. The final two algorithms we use, one is called PPMJXC, which stands for push, pop, move, jump, XOR, and call. Basically, the instruction ratio should be a push. There should be a high instruction ratio for push, pop, move, jump, XOR, and call. What we found in the real world is that, yes, without people knowing our algorithm and specific attacks, this proved true, that the shellcode, the injected threads were of this type and were a very high ratio. And the ratio is configurable. And finally, the one thing that x86 has to have is an ending signature or a control flow transfer. That is, there has to be a call at the end, there has to be a jump at the end, there has to be a return. It can't just keep going off into garbage memory. What this means is that our algorithm is going to be able to find the ending parts of shellcode, injected threads, and big portions of DLLs. So you're guaranteed to find a little part of it, and then if you do further analysis, you'll find the rest of the code above or below it. We have a 100% success rate in finding injected DLLs. Basically, injecting a DLL, there's too much code in memory for us to miss. We have a great success rate in finding shellcode and injected threads. I'm going to show you now, first demo, which is actually a malware that was found on a customer's computer. Can everyone see this? Are we? All right. What we have here is the process address space has been acquired. We have the DLLs in red. Known DLLs are in red, and executables. We then ran this, and the reason I didn't run this live for you is one of the problems is the runtime of this thing is very long, so we would have been sitting here for a while. So I pre-ran this. The green here indicates that we have possible x86 instructions that we consider valid. So if we go and disassemble it, first off, this is 9 instructions that we found out of the process address space successfully with no false positives. And we actually did reverse the malware to determine that this was what it was doing. So we know that this is valid. Basically, your get EIP commands are right here. They then figure out that there's a string. They push a flag, then they push the string, then they call winexec. And I'll just show you that it's an idle right here. And if we look right here, there's putting a command shell into Notepad in this case. So that is how successful we can be in finding such a small set of instructions. And really, you're not going to find a real-world instruction set that's much smaller than 9 instructions. Shellcode, the smallest you may find, Win shellcode, maybe 128 bytes, 256 bytes. So this is a pretty good indicator of the success we may have. All right, so that was find executable code. The tool that's being released in the URL that's right there that you guys can grab up is Memorize. It does more than just process acquisition. I'm just going to tell you really quickly what it does so I can get to my demos so that I can get you questions and stuff. It's going to acquire, it can do memory dumping. It can list loaded drivers. It can enumerate processes. Within the process enumeration, it can enumerate the handle table. You can see the files, things like that it has open. Enumerate memory sections, enumerate open ports. We understand how ports look in memory. We don't rely on no API calls for all of this. We do the parsing ourselves. We understand the kernel structures. We use strings in memory, which is a very revealing thing if you look at strings in memory for malware. We can acquire processes, and we can acquire drivers. So if you have a rootkit that's hiding itself on disk, and you don't want to bother unhooking it, just acquire it, and you'll get it in memory. We can detect hooks, and we use the page file when we're running on live memory. So that's a quick little blurb about Memorize. So the conclusion, the state of process acquisition was good, but wasn't great. We now have a way to acquire a complete process address space. There's still plenty of room for improvement. I'd like to implement my own IAT reconstruction for both drivers and user-learned processes, which is a little different from what I've seen with the Windows driver loader and the Windows PE loader. There appear to be some caveats. I want to improve our executable code identification to the point where we can run it in a real time. We want to parse files that are backed by themselves. Better post-process acquisition techniques. More stuff like find executable code. Maybe better string analysis, things like that. And the thing that we're saying now is that memory analysis in the forensic world and malware analysis are completely mutual. They have a lot of things in common that both fields want to do. So it's good to keep that in mind. So feel free to download the tool, use it, and now it's time for demos. What I will say is I've pre-done a bunch of the running stuff that may take some time. I had about 20 minutes to demo, and I only have 20 minutes of time left, and I want to get you guys to time for questions. So I may cut something short here. But demos, and if you have any questions or you want to ask me stuff further and you don't feel comfortable now, you want to see find executable code run on something else, feel free to stop me. I'm going to be here today and tomorrow, so I can answer those questions. All right, so all right, this is better. So when you install Memorize, you get these files. The batch files, I'm going to try to go through this quickly because I do know how much time I need and how much time I have. The batch files will actually execute Memorize, or you can execute Memorize from command line. You have to configure your XML files. So this XML file, it has the following. This is our memory acquisition. I'll show you this one. This is the actual full process acquisition audit. You can specify a PID right here, or the process name. Either one will work. And we can pull it out of a memory dump, so it doesn't need to be on live memory, which is a pretty nice thing, especially if you're doing forensics. So that's the acquire process, which is what we'll use. I'm going to do a demo here. I pulled this sample. Oh, I guess. Forgot a slide. The demo that I'm going to be doing here, the first one, is going to be here. We have a Themida packed binary, and Arrow is going to be talking about Themida and some other really cool packers in the next section, so I encourage you to stay. The binary, we're going to run Ollie debug first, then run the malware. We're going to see what happens. We're going to run the malware, then run Ollie, see what happens. And then we're going to acquire it because we can't acquire it using our traditional methods. And then I've already rerun the find executable code on Themida to discover some interesting things about Themida. So, So I'm running Ollie debug. This is the file. I got it off of offensive computing. I run it. It pops up a warning saying it's not going to execute because it already knows that there's a debugger running, which is pretty neat. All right, well, let's try to trick it and just kill Ollie real quick. I'm going to infect the machine now. Networking's disabled, and so is my host machine networking. So if you have any fears, do not. So we see it. It's doing a bunch of stuff here. And this is the actual lsas.exe. I was going to show you that lsas.exe is a Themida-packed binary. I was going to show you the difference in, actually, we'll try to do that real quick, actually. So lsas.exe exists at Windows System 32. So this is the file on disk. I'm not going to really let it finish analysis, but it's got two functions which are pretty unuseful to us. If we look at the strings, it's really not going to have anything that's useful to us. As a malware analyst, we have no clue what this binary is doing. We do know it's running in memory, and that's bad. So let's go back to our VM real quick. Let's run Ollie now. Let's just keep an eye on LSAS. We're running Ollie. Let's go to attach. It's found Ollie's running in memory. It just killed itself. So you can't even get Ollie up. If you did this with WinDebug, it doesn't kill itself on. It will just kill it when it tries to attach. So let's reinfect ourselves real quick. We'll wait for lsas.exe to finish running. We'll do process dd bat. You have a bunch of different command line options. I'm going to use the PID one. I want to acquire 1056. It's going to drop the files in this audits directory right here. Real quick, I'll draw your attention to a couple things. We determined from memory the major version of the operating system right there. And from memory, we also determine the minor version. So from both, we do it from memory, no API calls. We're able to determine both. And it's already acquired the process address space. So this is what the address space looked like for this binary. We've got, it's still acquiring, hold on. Okay, so here are all the DLLs that it had loaded. Here's the actual binary itself. We have our stacks and our heaps. So let's, I'm just going to, this was the LSAS on disk. Let's so it's going to be loading it up. I'm going to need to hit a couple buttons here. This acquired binary is 514 functions, so we know we've got it in a semi-unpacked state. Arrow's going to talk more about Themida, but real quick, Themida is a function-level encoder, so we know that we don't have a full look at it, but we have a good part, and a determined reverse engineer may be able to make sense of what's going on, partially. So it's going to do analysis. Oh, it's done. I'm going to run this real quick. I can show you some strings. While I'm doing that, I'm going to jump back into the VM real quick. I'm going to run another audit. This audit tells me about the process itself. I want to know its handles, its strings, its ports, stuff that I may not be able to get when I reverse, just any metadata that may help me and speed up the malware analysis process. So I'm going to turn on handles. I'm going to turn on sections. I'm going to turn on ports. And I'm going to turn on strings. This is going to run the memorize with these options. I've actually already run this audit and saved it so I can show it to you so we don't have to waste time. The end result here is